Well, thanks very much for the invitation. I'm looking forward to talking to you about C++. And I tried to come up with a title that maybe was quite provocative. So it's good to see so many of you here to come and see what I mean by this. So for me, one of the big challenges that as a community of people trying to use these large scale computers to do interesting and useful research and science is the challenge of actually programming the things and getting the best performance out of them. And that leads us to a question, which is, so what heterogeneous programming model should I use? And there are many options. And in recent history, I guess we've sort of seen it a little bit like this boxing match of which one is going to win out overall, which one's going to be the one that's going to last everything. And there's lots of pros and cons to this. Some of them are open standards, some of them are not. Some of them maybe are open source projects. Some nuance there between a standard versus an open source project, mainly in terms of governance. Who are the people behind the ship that's steering the progress of that parallel programming model is a difference there. Maybe they only support one vendor, maybe they support lots of different vendors, maybe they don't support GPUs at all, maybe they only support CPUs. And then is the syntax actually the same if you want to support different types of devices or not? And there's all these different choices and trade-offs. But throughout all of this sort of thing at the bottom left is this key observation that we start with a serial programming language, something like C or C++ or Fortran. And then because we want to program a large scale system, we add in MPI, and that gives us some distributed memory abstractions and message passing, all that good stuff. And then we also plug in a load of other stuff, whether it's directives or another framework or a programming model to enable us to program the multi-cores or the accelerators that are available on our node. So what's interesting then is that serial programming language is not serial anymore. And since the release of C++ 17, it builds in these abstractions for shared memory and accelerated parallel programming. So maybe the sort of research question that I had at the beginning was, maybe we don't need this blue box on the right-hand side. Maybe we can just get away with parallel C++ or parallel Fortran or whatever, and MPI for distributed memory. So this talk is about C++, but I should mention Fortran. C++, is the second here, right? It's Fortran got there first back in 2010. They added do concurrent to Fortran 2008. They also added coarrays. So maybe Fortran is just all you need, and C++ is nearly all you need. So obviously Fortran is a very important language. Many of the cycles in the UK national machines are running Fortran code. It's interesting that Fortran as a standard is still developing. With Fortran 2023 adding lots of extra features, mainly the reduction clause, the reduce clause, to do concurrent, sort of inspired by OpenMP, I guess, to help some of the challenges that the compilers were having with recognizing reductions. But yeah, today's the talk's about C++, but really it's this trend, I guess, is there where maybe the serial language that we start with isn't serial anymore, it's parallel. So I'm going to break this talk up into three kind of quick parts. I'm going to give quite a whistle-stop tour of some of the key features that happened in more recent versions of C++, which we'll go through just to sort of not really a full tutorial, but just enough to kind of let you know what all the words are and where to find the information and show you kind of how they work. I've then been using some of these features in some of the research in my group, and I'll show some results for that. And then finally, some more kind of thoughts around what's missing in C++, what you do when C++ doesn't get you all the way there, and some ideas around future directions. So let's start then with some C++ features. These are the 5 ones that I'm going to cover, and I'm going to go through them quite quickly, but give you enough information to kind of understand how they all work. I'm not going to talk about atomics and atomic refs, but they are really useful parts of the parallel abstractions that you need to build real applications. There's a use case that I'll talk about in the second part, where we were using atomic and mutexes and all that kind of stuff to program using C++, but I won't go into too much detail. It's just an abstraction around atomics. But the main features then I'll talk about are things like mdspan, things like algorithm and numeric, the libraries, along with the execution policies to make them run in parallel. Some utility things like ranges and views, which make all of that much easier to deal with. Then some more future-looking things that are coming soon, things like linear algebra, where C++ has BLAS, and senders and receivers, which is a more asynchronous execution model in C++. So first up then is mdspan. So this is introduced in C++ 23. Compilers are pretty good actually about supporting some features, and I'll give some links at the end around how you can get these things in compilers today. So there is a library from the Cocos team that implements mdspan in most of the major compilers. So mdspan is a non-owning view of the data. So it gives you a view into some data. Basically, it wraps a pointer and gives that pointer some extra metadata around how that pointer should be chopped up into a multidimensional array. It inherits from things like standard span. That's why it's called a span, as this non-owning view. So if you destroy the MD span, deconstruct that object, then the data doesn't go anywhere. It's just a wrapper around the pointer, basically. It defines all these things as template arguments. So the type of the data, double, single, whatever. The extent, so the amount of data in each dimension. So how many things in each of the dimensions. You can have basically as many as you like. And also with things like the ordering, that is called the layout, given by this layout policy template argument. By default, it's layout right, so the rightmost thing is moving quickest, so it's contiguous in memory, but it allows you to say switch between column major and row major data layouts just defined in its policy. And then this thing called an accessor, which is how you access the data given a one-dimensional index, and that allows you to do some kind of tricks basically with the MD span itself. So that's what it looks like. How do you actually use it? Well, this is basically just a simple example that fits on the slide. How would we initialize a two-dimensional matrix of size n by m? We just construct the span, the MD span, with my variable name matrix, and I give it the pointer and the two dimensions that were passed in as an argument to this function, and that's it. I can now construct this view, two-dimensional view, into this one-dimensional pointer data that's allocated there. What's nice is C++17 added this thing called CTAD, or class template argument deduction, which means I can just write it like this. Without CTAD, I have to spell it the long way around, which is like this, where I have to define a lot more of the template parameters. So I have to define these extents, which is the second template parameter. I have to define the type of the data that's in there. And notice here in the example, before this CTAD, it infers the type of my data is double because it knows that A is a double pointer. The compiler can figure all this stuff out for us. You can have extents that are fixed at compile time, or like here, which I think is mostly useful for HPC, where we don't really know how big our data is until we read it from a config file at runtime. These dynamic extents, which say, it's a runtime dependent value. But here there's two of them, two dynamic extents, so it's a two-dimensional MD span. So I can construct it the kind of simple way using that CTAD, the class template argument deduction, which is pretty convenient as a programmer. You don't actually have to write that much to use all these features. I can then loop over the MD span just as I would in a two-dimensional loop, so tightly nested loops. I can query the MD span for the extent in each dimension, so in the 0th dimension or in the first dimension. It matches the ordering that it was when it was constructed. And because of the layout, it's the rightmost one that is being iterated quickest in memory. So I do have to make sure that my loop order matches my layout. There's not a way to kind of connect the iteration space with the data layout. They're kind of two separate concepts. I think, what do your loops iterate over and what does your data laid out? And obviously for well-optimized code, you would like those to be in alignment, doing the same thing. We'd have to make sure that we write our code that way too. So I can loop over the two-dimensional view of my data, and then I can get at my data. So we now have this thing here, which might kind of look a little bit like Fortran again. We've just put a list of variables that index into the array itself, here I and j, in square brackets, just with a comma between the two. This is the multi-dimensional subscript operator. Some interesting history, I guess. In C++20, they knew mdspan was coming, so they wanted to enable notation like this, where you could just write square brackets I, comma j, to access element ij of the matrix, right? It feels a very natural way to use the user language and write this, but they had some problems because comma already means something in C, and so it means something in C++, the comma operator. So in C++20, they deprecated the use of the comma operator without parentheses around it in the subscript operator, so in the square brackets notation. So in C++20, this was deprecated, but it didn't mean what it looks like it means. It meant something different. And then in C++23, they added this multidimensional subscript operator, where the operator can take a multiple arguments. So this is just like a function call, syntax sugar for a function call. I'm looking at presenter view, so maybe the mouse doesn't follow. This I, comma j in the matrix is much more natural notation. But but it's called the multidimensional subscript operator, is the operator square brackets. So that's mdspan. It's quite nice. We finally have multidimensional data structures in C++. And yeah, there's lots of power that you have with these template arguments to be able to specialize and bring your own layouts. There are things like padded layouts or strided layouts that you can bring your own. You can make your own layout and specialize on that too. So that's mdspan. Moving on then to kind of actually parallel stuff. So this next thing we'll talk about is known as stdpar, but C++ calls it the algorithm and numeric libraries, and also part of the execution library, which we use the execution policies part of that execution library. This was all added in C++ 17, and it adds into the STL, the standard template library, this idea of this execution policy. So it builds on stuff that was already in the standard, basically things like transform reduce, for each n, sort, and all these kind of things. They now accept this execution policy. The way these algorithms work is that they apply a function, either a functor, a class with the operator parentheses, or a lambda function, which is just syntax sugar for one of those functors, to the elements of the iteration space that's being iterated over by one of those algorithms, the transform, reduce, or for each n. Basically, you could imagine you turn a loop, a standard for loop with a loop body in the curly braces into a std for each n with some arguments to explain how to iterate, and then you turn the loop body into a lambda function and pass that to the actual algorithm itself, the for each n. So it's kind of manipulating a regular for loop into this kind of more functional style of programming, then allows you to pass in this execution policy to say, well, execute that in parallel too. We can think about this in a couple of ways, either data-centric. So this is where you would, for imagine, iterate over the elements of a vector. So you don't remember which index you are. You just know that you have an independent bit of data that you've brought out of your container, your std vector. Or what's more useful, I think, for HPC is you need to remember where you are in the problem space. If you're doing a stencil code, you need to know that you're at ij, because you need to know your i+1, i-1, j+1, j-1, sort of a 5-point stencil approach. So you need to remember where you are. So there's ways to get the index and iterate over indices and access your data through the lambda function too. One important abstraction that they have is these are all synchronous execution. So it basically behaves like it always did before. You call this function. When the function returns, you know all the work is done. So the execution policies are the path basically for offloading the work to a GPU. But here it means that the host waits for that in each of those kernels to run. Basically, it's like having a wait after every kernel call. There's pros and cons. Maybe it's not too expensive for lots of use cases. Maybe it is. There's some ways around it that we can talk about in some later slides. But that's the model, at least. It executes the function just like a function call. When the function returns, the work is done. So this is what it looks like. This is DAXB, famous DAXB. It takes a vector and times each of the elements by a scalar value, so a times x, and I add that to the y vector. So adding two vectors together and timesing one of them by some scalar value. I could write this as a for loop, of course, but instead I use the stuff that's in C++ 17. The first of these is choosing a parallel algorithm. So for this is the kind of data-based approach, data-centric view. I pick transform. It takes two inputs and one output. So I've got x and y are my two inputs to this algorithm, and y is the thing I'm computing, is the output. So I pick std transform. I give it the range of the input. So here it's the pointer x, and that's the begin iterator is x, and my end iterator, the end of that extent, is x plus n. That's like pointer arithmetic. You can use pointers as iterators in C++. And then the second input is y, which I don't give a range because it picks it up from the first one. So it's on me to make sure that y is big enough, at least bigger than n. And then the output is y for that final, the fourth argument that's been highlighted in bold. So this then is going to then run n instances basically of this lambda function that's coming up next with the inputs from x and y and output y. My loop body is then this lambda function. It takes arguments kind of inferred from the data types of my inputs. So I can just use auto reference, which is nice. I don't have to worry about that. So here I've got auto reference x and auto reference y as the arguments to my lambda function. So that's the variables captured by the inputs that I'm available to use. I then have my DAXB expression using that data. So here you can see I don't remember where the I iterator of the loop would be here. It's all data centric. So it just takes the ith element, the capital X array called lowercase x, times it by alpha and adds it to the lowercase y. I return this out of my lambda function, and that then sets like a memcopy into the y output variable that I listed in the transform function. I also have to capture variables that are needed inside the lambda function using the lambda capture rules. So inside the square brackets, I've got an equal sign. That's going to capture all the other variables that I need, basically alpha. So wherever alpha is defined as the scalar value is going to capture that by value. So it's going to make a scalar copy of that, just as we would pass that as a kernel argument, say in CUDA or OpenCL or something. Then to make it run in parallel, I just add an execution policy. So I spell this std execution par on seek, and then depending on the compiler, this will then run this lambda function n times for each of the elements of x on a GPU or a CPU. It's kind of the control that we have is at that when we compile level. So for a given file, the compiler could then put all of the par on seek executions on the CPU in parallel or on the GPU in parallel. It's up to the compiler basically to choose that for us. We can't selectively do it programmatically with this model. But for many use cases, this is just enough. I just say this is basically a big parallel loop, and the compiler will then generate the GPU code and offload it to the GPU as a kernel, and then wait for the result to be returned. And there's lots of stuff that we can do with this, just with this model, where with transform, with for each n, transform, reduce, and par on seek, you can get a long way with just those routines. Just a quick note about the execution policy. C++ comes with 4. They're listed in the table here: seek, unseek, par, and par unseek. The wording that C++ uses in the standard for the words concurrent and the words parallel are not really aligned with how the HPC community typically uses those words, in my opinion. So it is kind of an odd read if you want to read the C++ standard. You're sort of reading these words, then really they don't mean parallel, they mean something else. But here, at least, I've tried to use the HPC version of the words that we know what they mean. With the sequential execution policy, seek, this basically just means the thread that called the function, say transform, iterates all iterations of the loop. It's sequential execution, business as usual, just as it was before we had the execution policies. Then unseek allows that loop that's sort of implied by the transform and for each to be vectorized with SIMD instructions. What this really means is that lambda function, you're allowed to interleave iterations of that lambda function with other iterations of that lambda function. So you can do, say in the DAXB example, you can do the multiplication with a scalar on several iterations of the loop before adding the result of that to the y, for example. So you're allowed to interleave in a kind of SIMD style those iterations. So multiple of the iterations make progress before they make later progress in the same kind of iteration of the function call itself. We then have the parallel execution policy, so std execution par. This then unlocks the multi-threading. This enables us to run in multiple threads. What this means is this is what we really mean by concurrent in kind of HPC or parallel programming terminology, where the iterations can be reordered in any order. It doesn't matter. We can run the loop forwards, backwards, all the even ones or the odd ones. It doesn't matter. We still get the correct answer, and we can assign those to threads. But here, the parallel execution policy comes with really strong guarantees around the behavior. It basically means that once a thread starts running, it will continue to run. So once it makes a step through your program, it continues to make further steps. This means that we can use things like atomics, atomic ref, mutexes, and build these starvation-free algorithms. Basically, we can have those threads communicate with each other through atomics and mutexes, that kind of thing, locks, that stuff. Par unseek basically applies both parallel and unseek. It's the way of spelling this as a big parallel loop with no dependencies. This has a very weak execution model, basically. It's called weakly parallel forward progress in C++ language. It basically means that once one of the threads has made some progress, made a step, that another thread will maybe eventually make some progress at some point. But that means then there's no guarantees if one of those threads holds a mutex or a lock or something, that it will ever be scheduled again to release that lock, so you can deadlock your program, basically. Yeah, the forward progress guarantees of par and seek and kind of from unseek mean that we can't write those algorithms with atomics and locks and things. So we need you need the stronger guarantees of parallel. Throughout all of this, though, we are really just promising the compiler that the lambda function that we gave in is basically free of data races. It's not going to deadlock. We're respecting the rules of the language, which is what we've always done when we've written programs. It's like a contract between the programmer and the language designers where we promise to write correct C++ code or C code or Fortran code. Otherwise, the compiler will compile it wrong. So these execution policies are pretty powerful. Most of the time we use par on seek because it's just a big parallel loop. But as I'll show you soon, we can use par, the parallel execution policy, to do some quite interesting things. So that's what's known as std_par, the kind of parallel algorithms that are available in C++ 17. One thing that is missing, though, is this convenient way of looping over an iteration space rather than looping over data. So when we write a normal for loop, we say, for I equals 0, I is less than n, I plus plus. We know our loop iteration variable I. We remember and can use the value of I inside our loop. But the data-centric doesn't give us that value. We really want access to that loop iteration variable. And this was an awkward without the stuff that came in C++ 20. We basically had to list all the integers that we needed to and read them from memory, or do some clever tricks that then became stuff that looks like ranges. Ranges basically give us an abstraction over iterators. It has a thing that has a start and an end, and we can count our way through it. And you can use that basically to give you a lightweight list of integers to iterate over. It's very much like the yield in Python. So in Python, you can yield the results of a function. So then it just keeps spitting one out sort of on demand. It's lazily evaluated, and it has small storage rather than the extent of the iterator. The two key things for HPC are the iota view and the Cartesian product view. Iota gives us a list of numbers from the beginning to the end, and the Cartesian product builds like a multi-dimensional iteration space of those things. It kind of roughly looks like this. It's quite tricky to get it all to line up, but this is that same init map routine that I showed you earlier with the mdspan. So now I'm kind of building all things together. I can change my doubly nested loop to this for each with a parallel execution policy. I can just initialize all elements of the matrix at the same time. And I do that using this Cartesian product and the iota view. So here I've got two lines with std views iota, and they give me a counting iterator basically from 0 to n in the first instance and 0 to m in the second instance based on the construction of my mdspan. Then I build a Cartesian product of those, which builds my two-dimensional space of n by m things to iterate over. And I can just pass that directly as the range to iterate over in my for each n. So here I have cp.begin and cp.end. That's what we're looking at basically. What that gives me then is like a two-dimensional object, my ID, which specifies my point in this Cartesian product space. And then I can use in C++ this thing called structured binding, where I pull out of the ID my I and j variables again. So this is the auto square brackets I, comma j. That pulls out the ID, breaks it back up into the two parts in the Cartesian product. So yeah, this is quite powerful. You can obviously imagine multi-dimensional parallel spaces here defined then, and you're just saying it's all parallel. It's kind of quite a convenient notation. It means that I can iterate over indices in parallel and use as many different data arrays as I like, rather than just be limited by, say, 2 input arrays if I want to do the data-centric view of things. So that's ranges. It makes the parallel algorithms that were in C++ 17 a lot more kind of user-friendly for this index-based parallel programming. Looking forward then, so we're sat in this talk in 2025 and we're talking about C++ 26. And all of these things in C++ 26 have already made their way onto CPP reference. So we can be pretty sure that they're going to be coming in the finally ratified version of C++ 26. But yeah, subject to change. Maybe there'll be some last minute changes here. The first of these is linalg, the linear algebra library that's coming to C++ 26. This basically brings BLAS to C++. What's nice is it builds on top of the mdspan data structure. So you define your matrices and vectors using mdspan. And this means that you have all that layout information and sizes and extents kind of saved in there. And with the layouts, they bring some extra layouts that allow you to talk about transposed matrices, or take the complex conjugate of the complex data that's stored in the matrix, structures for lower and upper triangular and diagonal matrices. You can kind of build all this into that mdspan abstraction just with the layouts and the accessor policy, basically. They also build off on top of the C++17 execution policies, because you can then pass an execution policy into the BLAS routine. So you can say, execute this in parallel across all my threads or on my GPU, which is really nice. What this means then is matrix multiplication is going to look like this, right, on the slide. I make my 3 matrices using the mdspan notation. So this is the standard. I want to get an m by n matrix out, with p as my intermediate direction of the matrix. I built my 3 matrices. I then call std matrix product that computes a times b and stores it in C, just with those arguments there. Notice, and I've put I'm not picking necessarily on any BLAS implementation, but this is how I would have to write this in 1MKL with the C interface. I have to have all these arguments here, which are very, very easy. If you've ever tried to do this from scratch a few times, it's very easy to mess up the order of all these arguments. You have to remember which way round your matrices are, whether you're transposing them. You have to repeat the size of the matrix in many places so that you get the strided data access correctly. So you can see here that A and B and C are listed once, but I have the sizes M, N, and P in several different places in my function call. Kind of all this stuff is known information. If only the pointer could store its information about how big like how many dimensions it had, how big it was, and which way around the data was stored. And that's basically what mdspan gives us. So that's pretty nice. We can just have these matrix products here. You'll notice here that it doesn't have the alpha and beta parameters, but you can build that in with level 1 BLAS, and hopefully the compiler is smart enough to figure some of this out. To make it then run in parallel, I just add an execution policy on the front. So this would now, if I had a compiler which supported linear algebra and this C++17 parallel unsequence, this would then be able to run this on a GPU. Functionally, a good implementation would just be replacing the C++ library call with the MKL or cuBLAS call or whatever your vendor library was underneath as the library implementation. Just kind of stitches the pieces together. That's the hope. But that's pretty cool. We're able to now have BLAS directly just in C++. And it unifies that interface between all those BLAS libraries too. The final feature to talk about then is what's coming soon in C++26. It's known as senders and receivers, but it forms part of this std execution library. We've already seen part of that with the execution policies, and this is kind of the rest of it. This kind of breaks away from the parallel algorithms and this idea that it's just a function call and it's a synchronous behavior, with this ability to build a task graph that has asynchronous execution. It gives us the ability to start to control where parallel work happens. So we have this idea of a scheduler, which gives us a control of where things start to run. So rather than just in threads and either all of them or none of them based on the compile time flag, we can then do this more programmatically. Things like thread pool, inline scheduler, things like GPU scheduler allow us to then articulate in our programs where a task graph should be executed, where there's a chain of kernel calls, basically. It gives us quite a lot of bits. The main bit is senders, a way of describing senders. You can think of these like tasks, and it gives you the mechanisms for building up those tasks into a task graph. You can think of them, if you can remember C++ futures, they're a little bit like that. A sender gives you back a value and maybe an error, but it describes the work to do. But unlike a future, it's a handle to work that will be scheduled later. A future is just a thing that's been scheduled. You need to remember that it's been scheduled and wait for it later. But here it's saying, here's a thing, schedule it later. You can compose them with this pipe syntax. So you pipe all these senders together, and that means that you've got a pretty kind of compact notation for doing this. It is senders and receivers. They come in pairs, but you never write a sender. You never write a receiver, basically. It's hidden from code. It basically handles what the senders return, the value and the error, but we don't really see them in programs. It's kind of the glue that holds things all together. So what do we see in user code? Basically is the things at the bottom of this slide, things called sender adapters. This is basically the description of the task graph. Do this, then do that. So you have a then object that you plug in the new task and the old task, and it gives you a new sender that shows that you should do the first thing, then the second thing. Things like bulk is the equivalent of like a for each n, where you can say do all of these things in parallel as a big parallel loop, and you embed that inside the task graph. So this is the way of getting big parallel kernels running inside that task graph with bulk. We then have to kick off our task graph, and for this we have this scheduler sender factory, basically is the entry point, And then we need the exit point, which is this sender consumer, the thing that takes in all our final senders and actually starts the work. We build this task graph, but we never actually start running it until something waits for it to start. And for that, we have this thing called sync wait, where you basically make the calling thread stop and wait for all the data, all the tasks to be run. That's a lot of words, and it makes it sound a lot more complicated than it is. So this is an example from the P2300. This is the standard. The way the standard works is people write papers, and the paper that proposed senders and receivers is called P2300. So this is their hello world example. It's not quite vector add, which is a bit disappointing because that's our hello world in HPC, but it basically is enough. It adds two numbers together in a task. So we start things off by a scheduler. So we say run this in a one of the threads in a pool, some other thread than the thread that's executing this code. And we then now have our sender to kick things off, basically, our sender factory. So we plug our schedule into this schedule, SCH into the schedule, and that gives us this sender called begin. That's the beginning of our task graph, like the top node. That it doesn't really do anything, it just starts us off. It gives us that handle to put more work onto. I then put my first task on. This first task prints hello world, and then it returns the number 13. This is producing a value. It's producing the number 13. This is where we see then. I say you can see the then sender adapter. It takes the begin sender and it takes a function or a lambda function to do something after begin has finished. Here it's going to be the print and the returning of the value. And then I put another one again using the same notation. So then after I do this, which has an input from the previous sender. So you see that as an input argument in the lambda function, int arg, and it adds 42 to that and returns that. And at this point, all we've done is build this chain of tasks, my begin task, my high task, my add 42 task, but nothing's happened yet. I now need to make the thread that is executing all this task building starts and kicks the graph off and starts it running. So we say this thread needs to wait on that final sender, the add 42 sender, and then pull the value out of it. So here, this would basically set I, the variable I, to 55, 13 plus 42. So this is quite powerful. There's lots of ways of adding more schedulers in here. So you can have senders that continue on other schedulers. So you can do some work on a CPU, then do some work on a GPU, asynchronously queue up more work on the CPU in the meantime, and bring everything back at the end and have cross dependencies between all of that work. It's a very powerful task graph that we're building up here. So this is all kind of coming soon, but is kind of a way of unlocking that need for the CPU to offload to the GPU and have to wait for the result every time. It's much more heterogeneous programming that we're used to with all of the other parallel programming models. So that's the last of the kind of things I wanted to go through and kind of technically. And really, this slide is just here as a way to show that there is good support already for lots of this stuff. Lots of libraries. It's all mostly in the library, so you can bring your own implementation from the links at the top. And many compilers have already good support. And these are the flags basically that you need to turn it on. So that's the theory. What about the practice? So we've been playing with some of these features for quite a long time, and I'm just going to kind of highlight some of the results that we've had. I'm going to start off with the world's most boring graph, which shows that basically whatever programming model you pick, you get the same result. For triad from Babelstream across the GPUs from 3 different vendors. The graph is showing percentage of theoretical peak main memory bandwidth, and the different bars are different parallel programming models. Studpar here is the standard C++ stuff that I've been showing you, and it's kind of a good representation that it basically doesn't really matter what programming model that you use for this, you get the same performance. So that stream, it's pretty simple. It's just triad. It's like DAXB. Not that hard for a compiler to get right, you would hope. It's a good litmus test, a good canary to make sure that it is actually going to get the right answers and perform well for more complicated things. But shows that this is possible, which was nice to see. We then tried this with other mini apps and proxy apps, things like Cloverleaf. It's memory bandwidth bound. That's on the left. Things like Minibud, which is a molecular docking code. It's definitely compute bound. It's single precision, and that's shown on the right-hand side. In both cases, lower is better. And which in the heat map, it's the CPU performance and the GPU performance is in the bar charts. And again, it shows that basically you get comparable performance using this to the CUDA or the HIP or whatever the lower level implementation is with the C++17 parallel algorithms. There were some caveats, some little bugs that we found in the compilers and libraries. The details of that are in the paper, but once you fix those, then, or once, here in Intel and NVIDIA fixed those, then the performance was much more in line too. And this just uses the iota views from ranges, things like for each n and the par on seek, and we can build things like Cloverleaf, things like mini Bude, which is good and do useful stuff just with those building blocks. We can do more. We had a really interesting study that we worked with NVIDIA on around implementing Barnes-Hut for an n-body approximation. This was interesting because this is a summary of Barnes-Hut, but rather than having all particles, the kind of pinky white blobs, updating their position by some number from all of the other ones, you make this approximation and do the local things accurately and have an approximation for the far range interactions. To do this well, you basically need to build an octree that is unstructured in some way. It's not a balanced octree necessarily. It depends where your particles are. You have to rebuild this every time step. And whilst it's not the most expensive step in the Barnes-Hut algorithm, if you have to keep doing this on the CPU and shuffling the data around it, it can be quite expensive. So in this work, we built the octree on the GPU. We did this using standard parallel algorithms. The algorithm that we had was that threads were inserting bodies into this tree. So they're collaboratively building this data structure all on the GPU using for each with the execution par. And to do this, it needs atomics and locks, basically. That's why we had to use the par. Once you have the octree, you then need to aggregate all these particles together. So the yellow blobs in this picture, you have to calculate like the centroid of mass of all the particles in the level of the tree. And again, we can do this in C++. We had some fun algorithms where we made lots of threads. Most of them just had a big early exit. It was quicker to say, launch all threads for all of the nodes in my octree. And if they weren't a leaf node, just to finish and let the leaf nodes continue, than it was to kind of find them in the first place. With lots of threads on a GPU, that was fine. Still plenty of work to do. And then those threads race up the tree, basically. And the last one there gets stuck with the work of actually computing the mass on its way. And the update forces just a regular par and seek. The results of this were good. The right-hand side shows 4 different algorithms, basically the standard n-squared all pairs, with a couple of n-log n approaches, the octree, and then a bounding volume hierarchy. The first thing to show is that you pick a better algorithm, you go from n-squared to n-log n, you go faster. That's kind of not that interesting, I guess. That's where the purple to the blue and green comes from. But even so, what was interesting is having par, having the ability for a GPU to do par and have this octree saves you more work in the future by reducing some of those force pair computations. You do less work with the octree overall. This approach was faster than some other approaches that we found that built the tree on the GPU, but in 2 phases. You have to launch 2 kernels, basically. This was all just done in one, which was kind of fun. So you can, rather than just big parallel loops, this was interesting because it was a more kind of unstructured way of threads all racing up an unstructured data structure that it was building as it was going, like building the scaffolding as it was running up it, which was fun to do. So this all sounds great, but actually it's worth just saying there are some gaps in C++, and there are some things to kind of highlight from that. I like to think about all parallel programming models as defining these 3 abstractions. They give you a way to find out what devices you have and control where stuff happens to them, what compute they do. You have to have some way of controlling where your data lives, especially if you've got multiple memory spaces. And then you also have to be able to express parallel work. And C++ basically does the left thing and the right thing. And the middle thing, it doesn't really do at all. So the right-hand thing is all this C++ 17 standard algorithms with the execution policies. That's expressing parallel and concurrent work. The left-hand one of devices, that's basically where stuff should run. That's coming in C++ 26 with senders and receivers and the schedulers, but I can't really introspect my platform like you could say in OpenCL or SYCL or something. You can't figure out what devices you have and then make decisions based on those. The thing in the middle, though, is kind of the biggest Achilles heel, is that C++ requires and assumes that you have implicit unified shared memory for your systems, and the compiler and the operating system and the runtime, or even the hardware, has to make sure that that's true. The host CPU thread that's running your C++ program and the GPU that's attached, they can all see and share that very same memory. And C++ is unlikely to ever change that model. It's very embedded into how C++ thinks about its data. But hardware is enabling this for us. Yeah, the interconnects between our devices are definitely growing to make that happen. How does this compare to other models is also useful. So one of my students put together this really fantastic table comparing a bunch of different parallel programming models. And C++ is kind of mostly comparable to some of the other ones, things like OpenMP and SYCL, which give you full control of all of these things, with the exception, of course, of the how data is accessed, where data lives. So yeah, this is an interesting table to study if you want to kind of compare the difference between, at least in that model of abstraction, between those different models. Some other kind of gaps which are found as you start to use this kind of for real applications is that we now have two views of parallel worlds. We've got this algorithms and numeric, and we've got senders and schedulers, but they're kind of incompatible with each other. You can't use them together. The main gap for this is there's no reductions in the senders receivers model, but we need that for HPC a lot. Most of our codes are dot products for many of the matrix operations, especially sparse linear solvers. It's basically just dot products. And that's kind of a challenge. There are proposals to bring these worlds together. They're listed on the slide. The other challenge is in the hardware. Not all devices actually support PAR. All CPUs do. All GPUs from NVIDIA since Volta in 2017 support PAR, but other GPUs don't support this parallel execution policy. Even though they can support atomics through the other parallel programming models, the way that C++ talks about the requirements for parallel are much stronger, and they don't have that in the hardware, basically. But everything can support PAR and seek, and as we showed, you can get quite a lot of stuff done with PAR and seek. So if you do have a use case like that, what can you do? And the best way I think that I found is you can pick and choose. Use C++ where you can, and then plug in the different parallel program model to fill the gap for now. So you do C++ plus SYCL or C++ plus OpenMP just to fill in the gap where you can't make it work. There's lots of ongoing work within those standards to make sure that they can speak C++, that they align with the execution and memory models of the parent language, so that this is a thing that's viable in theory, but also in practice. So in the compiler, there's a lot of work in interoperability of parallel programming models. So in the lib offload library in LLVM, used to be called libomp target. It now is much more interoperable no matter which programming model that you have. If you haven't read the paper from Johannes Dofer, it's worth a read. He was doing some really cool stuff in there about interoperating different programming models, CUDA and OpenMP specifically in that paper. And then in NVHPC, for example, you can just pick and choose between std C++, OpenMP, OpenACC, CUDA. You can mix it all up together and it all kind of works because the compiler glues all these things together. That's it. That's kind of a whistle-stop tour through C++, the features that are useful for HPC, and some of the really interesting algorithms and applications that we can run. Here's the links to the kind of the research that I mentioned in the paper and where the results have come from if you'd like to know more. So yeah, happy to take some questions after if anyone has any. Thanks.
Hey, first of all, thank you for the interesting talk. I mean, you kind of mentioned it already in this middle box with this Achilles heel of all of this, but I was asking myself the whole time, basically, when you do this whole seek parallel thing, how can I take care of the load balancing or the thread affinity in general? How can I take care of first touch policy and all this? Is there a workaround, or do I have to use some additional layer on top of C++?
Yeah, that's a great question. So first touch is an interesting thing anyway, because it's really first touch policy is from the operating system and the memory allocator. Basically, the memory allocator mechanism says that the first time whatever thread touches that data for the first time, that's where I'm going to allocate those pages, right? So a lot of programming models don't really control that mechanism, and you use other effects like making sure threads stick to the same core to make sure that that's always true. So you pin your threads and have the affinity. The same will be true in C++ for the performance. What's interesting is most of the performance C++ implementations, they're implemented on top of OpenMP. So you would use your OpenMP thread binding environment variables to then bind your C++ program as it was running. Some of them are implemented on top of TBB as well for CPUs. And there are ways to try to get TBB to have good affinity as well. So yeah, we're really thinking in a higher level of abstraction here with C++. But yeah, the mechanism is you would still do the same thing, parallelize your initialization with the same execution policy or the same range as you would the compute kernels too.
Maybe if I'm allowed to ask a follow-up, Gerd?
Yeah, of course, sure.
Also, applying a certain schedule, I know it from OpenMP, is not possible, right?
I missed that with schedule.
Schedule, static, dynamic, guided.
Yeah.
All of this.
Yep. There's no abstraction for that in this. It's just, for the for the parallel and unsequenced, it's just uniform work for that lambda function. Yeah, if it was imbalanced, you don't have that control.
Okay, there's some questions in the chat. Let me continue with that. So Ian asks, with the C++ matrix operations, are compilers actually implementing this as a BLAS wrapper, or are they just doing internal implementations?
Yeah, that's a good question. I guess I don't know the answer to that. It would seem not cost effective to re-implement a BLAS library if you already have a BLAS library. So I would have assumed that most vendors would just basically write a shim layer that like takes the C++ thing and calls the vendor library underneath. It was designed like that to be able to just call the BLAS library. So some implementations, of course, like GNU or LVM could provide their own like reference BLAS implementation, or they could use OpenBLAS or one of the easy accessed open source ones. But yeah, the design was that it would do that. So if it doesn't, that's a good reason to complain to your compiler vendor to say that the BLAS performance is not as good as the library. So we would expect that to happen.
Hello. Thank you very much for the presentation. So my question is more general for abstractions, not only for C++ and others. We have a portability between CPUs and the GPUs. But when it comes to vectorization techniques or memory access patterns, CPUs and the GPUs are completely different. So a single thread has access to multiple data in SIMD in CPUs. But when it comes to GPUs, it's the consecutive threads are there. This is the most optimal way. But portability sense, it is not most optimal, I guess, for the model. So are there any like research or some other cases that bring even more portability between CPU, GPUs, or what is the best practices for when we target both CPU and the GPU? So yeah, I want to just ask you.
Yeah, that's a really great question. So in a lot of the work that we've done, and especially in C++, we use the same code on both CPUs and GPUs. This was true for the Barnes hut that I showed. It was just the very same code, but also things like minibud, Cloverleaf, Babel Stream. It is the very same code that is running, same data layout, same execution policy. Really, it then comes down to the sort of internal scheduling, and the compilers are doing a good job, and the runtimes are doing a good job to kind of chunk your work up for CPU threads or thread blocks and threads on GPUs. And really, for these big parallel loops, if you just have stride one memory access and access the data in the same order, then that is portable performance across both CPUs and GPUs in many cases, as long as it's vectorizing and the scheduling is done quite right. At least that's what we've found for our codes that we've tried. That's not always the case, and this is where the layout in mdspan is trying to fix. If you're familiar with Cocos, they have this idea of like layout left and layout right, and that's ported into mdspan, and they do that to try to make sure the memory access pattern on GPUs is sensible for these multi-dimensional parallel data structures.
Yeah, thank you very much.
I think the next question in the chat goes in a similar direction. As you said, loop order in nests is critical. How much control over execution order is available when using Cartesian products over ranges?
Yeah, that's a good question. So I think, you do have to match the execution order with the data layout. That's not an unusual request because that's what we do with all of the other parallel programming models anyway. They're not kind of tightly coupled together in that way. You can have a data layout and an iteration pattern that's completely opposite to each other and get really bad performance, and change once and they align and it's there. I believe they planned the Cartesian product to be able to do some sort of what amounts to like a tiling optimization, and you can obviously do that with mdspan with the layout. You can define the layout as a tile, like in tiled blocks through that too, and they've been designed for these things to be plugged together. Whether that made it into C++20 or not, I'm not sure, but it was on the roadmap at one point to be able to really describe what your execution, how that 2D or ND linear Cartesian product linearizes into a one-dimensional loop. I think that's in there.
I have a question about execution policies. So does the seek or par policies actually rule out SIMD? So if I don't use unseek, is SIMD rule out?
Yes, that's right. So you have to use unseek to get the SIMD, because what you're trying to do when you do SIMD, as you know, you want to execute like the first instruction of the first iteration at exactly the same time as the first instruction of the second iteration. Like if they're both a memory load, you load all, if you've got 16 wide vectors, you load iteration 0 to 15 as one memory load all in one go. So you're doing a bit of 15 different things, and parallel forbids you to do that. Basically, you have to go down one thread to the end before you can go down to the other. You're not allowed to interleave the operations from different threads together. So yeah, you need unseek for the vectorization.
Another one from the chat. Do we have a reporting mechanism on the compiler side to observe thread behavior or parallelism success?
That's always a great question. That is not a question unique to C++. All programming models, you would want to ask your compiler this question. So for that, it becomes a quality of implementation issue. Depends on the compiler reports, depends on the profiling tools, all that kind of stuff that we're used to with everything else. What's great actually about C++ with the implementations is it's implemented on stuff that we already know. So we already know how to look at how an OpenMP code is behaving, or a CUDA code, or other things, right? And we can use all the same tools just to interrogate your C++ code as well, because it's all implemented in the runtime with the same behavior. The challenge then is how do you get an unnamed Lambda function appearing in a profiler with a name you can recognize, but the tooling vendors are working hard so that at least it gives you the file and the line number from where that Lambda function came from, so you can like piece the information together. Naming things in computer science, as we know, is really hard. Maybe naming Lambda functions correctly is even harder. But yeah, the tooling is pretty good actually. So particularly if you use the NVIDIA compiler, the NVIDIA NSYS, there's a lot of good glue basically that means that you can pick out all that information.
You could add something to the standard that would allow you to attach a label to a Lambda function just to give it a name for the purpose of the profile.
Yeah, that would be nice. Yeah,
Name sense of organization.
Yeah.
Okay, one last question from me. On slide 33, where you presented the octree, the Barnes-Hutt results.
Yeah.
I noticed there were no octree results for AMD GPUs. Was that a limitation of the environment?
Yes. So there was no octree. The only GPUs we could run the octree implementation on was NVIDIA, because that's the only GPU that has the hardware support for the parallel forward progress guarantees needed by PAR, which is why we tried the other approach with this bounding volume hierarchy approach, because that just needs PAR and seek. So at least we could get GPU results everywhere. But for the octree construction, we needed atomics and locks and things. So we needed PAR, and only NVIDIA gives you PAR for C++. We did try it because, I don't know, we just thought maybe sometimes we might get lucky and atomics would kind of happen okay, but it really didn't. We reliably hung both Intel and AMD GPUs by running that code on, we just changed PAR to PAR and seek and hope for the best, right? But it reliably hung both of the other GPUs. They really don't have the hardware to make it work. The results are missing because the hardware doesn't do it. It wasn't a software or platform issue. It was the hardware limitation.
Okay, thank you.